Okay. We will do some revision on this JC1 topic. Okay, so we will actually go very fast. Okay, so if you have H3 plus, so H, proton number, okay, the proton is going to be 1 for each. So proton is going to be 1. Okay, and then 3 protons. Okay, so 3 protons. And then neutron wise, okay, neutron is going to be 1 minus 1, 0. Okay, 0, 0. So you add, it's going to be 0. Electron wise, okay, electron will be the same as proton. So you see 1, 1, 1, supposed to be 3. But because it's a plus ion, yeah, cation, so they have lost 1 electron. So 3 electron, you lost with 1 electron. So that's going to be 2 electrons there. So the answer is going to be D. Okay, next question. Now, for the next question. So here we just need to look at the relative atomic mass. You can calculate. Okay, so it's 3 out of 100. Okay, times 112. Okay, plus 56 over 100 times 114. And then plus 41 over 100. Okay, times 115. If you calculate this, okay, quickly you calculate, you will get D as your answer. Quite important to actually check, okay, is it actually, when you add all these 3, are you getting 100%? Okay, if not, then you have to be divided less than 100. But anyway, in this case, it's 100%. Now, so what is the equation for the second ionization energy of nitrogen? Okay, do remember, if it is second ionization energy of nitrogen, they have removed, okay, 1 electron from nitrogen. So it means we are looking at N plus, okay, N plus. So you can see here, all these are wrong. Okay, so N plus in gas, you're removing 1 more electron, so to give you an N2 plus. So do remember, all of them must be gas also. Yeah, so this is going to be D. Next question. So this graph shows the first 13 ionization energy for element Z. Now they didn't say that all the 13, it's just first 13. So anyway, if you have this element Z over there, so when you remove the electron, you always remove the outermost electron. So here, when you remove 1 electron and then you remove the second electron, the third electron, it takes a bigger jump over there. So that bigger jump indicates that the third electron is in the inner shell, okay, in the inner shell. So these 2 electrons are at the outer shell, or the outermost electrons. So these outermost electrons are going to determine the group. So you can see here is going to be 2. So it's supposed to be belongs to group 2. Okay, no need to look at the other things. Yeah. So that's going to be the answer. Next, number 5. The electronic configuration of 2 outermost shell, okay, is given. Okay, this is a special case because when you look at 3D54S1, it's supposed to be, okay, 4S2, 3D4. So you go and look at your periodic table, which one's supposed to give you this, but they actually change it into this, which is going to be more stable if it is written in this way. So if you look at your periodic table, there are 2 elements that we have learned under period 3. Okay, that will follow this pattern, which is going to be chromium and copper. Okay, chromium is supposed to be 4S2, 3D4. So you actually have this. But for copper, okay, it's supposed to be 4S2, 3D9. And we don't write it in this way. We write it in this form, 4S1, 3D10. That is more stable. Okay, so take note of this. Okay, so in this case, okay, the answer for this is going to be chromium. Okay, that's going to be the answer. The next, okay, the outermost electron in an atom of chlorine occupies a particular orbital. Which row shows the relative energy and the shape of this orbital? So if you look at chlorine, chlorine is 17. So I write down 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so if I look at this, this is 2 electron and then 3p5. Okay, you have the 5 electrons. So if they are talking about, okay, when they mention about orbital, okay, the outermost electron occupies a particular orbital. Okay, and then which one shows the relative energy and the shape of this orbital. So orbital, in this case, do remember this 3p, okay, they are known as subshell. So when we are talking about orbital, probably they're talking about as individual orbital, yeah, individual orbital. So these outermost electrons, they are actually at this orbital of each of the orbital over there. And then there are other orbitals as well. Okay, this is 3s orbital. So there are total 7 outermost electrons. Okay, 7 outermost electrons. So 2 in 3s and then 5 in 3p. Yeah, so subshell. Yeah, so we are talking about orbital now. So if we are talking about orbital, I think we need to compare between 3s and 3p. So 3s and 3p, we know that this is going to be 3p is actually slightly higher than 3s, the energy level. So therefore, you can actually say that the 3p is higher or can be equal. Okay, higher can be equal, but you cannot say lower or equal. Okay, because 3p is generally higher, slightly higher than 3s. Okay, so therefore, okay, A or B. But if you look at this, okay, the orbital, yeah, the orbital that they occupy, the outermost towards the end, okay, the orbital that they occupy will be more towards the 3p. Yeah, so the 3p, the shape of orbital that we are talking about is going to be the p orbital rather than talking about the 3s. Yeah, 3s or s orbitals, they are spherical shape. So in this case, the answer will be A. Next question. Now, which statement about 3p orbital is correct? So do remember 3p, yeah? So if you have 3p, okay, these are 3p, okay? They have orbitals. How many orbitals? They have 1, 2, 3, 3 orbitals, okay? So it can hold a maximum of 6 electrons, okay? Now, since they mentioned about 3p orbital, okay, 3p orbital, this is not 3p 3p subshell, okay, so it's 3p orbital. So one of the 3p orbital, they can only hold a maximum of 2 electrons. So this one will not be accurate to actually tell that it can hold a maximum of 6 electrons. Okay, it should not be written in that way. It has highest energy of the orbitals with the principal. Okay, let's continue again. Okay, so when we look at the 3p, okay, it can hold a maximum of 6 electrons. That will be wrong. It can only hold a maximum of 2 electrons here. So it has the highest energy of orbital with principal quantum number 3, not really, 3s, 3p, and then we have 3d. 3d is going to be the highest. Yeah, it has a higher energy level than 3s, which is correct. Okay, but it has the same shape. No. Okay, the 3s is going to be spherical, 3p is going to be a dumbbell shape, so that will not be the answer as well. Okay, it is occupied by 1 electron in an isolated phosphorus atom. So let's say isolated phosphorus atom means P. So if it is P, phosphorus is 15. So if I write down 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so okay, let me check here, 3p3, sorry. So 3p3. So when I draw, okay, so I will have 1, 1, 1. Okay, when we say it is occupied by 1 electron, okay, in an isolated phosphorus atom, yes, in this particular orbital, there is only 1 electron. So that's going to be the answer for 7. Okay. Next, which formula represents the empirical formula for a compound? The empirical formula is the simplest ratio. So this is going to be 1, 4, 1. Okay, cannot be divided anymore. So that's going to be the answer A. Which of the following is not a feature of metallic copper? Okay, this one will be anion cation, localized electron, lattice structure should be a feature. Okay, next. Silver and iodine are both shiny crystalline solids. Okay, which forces exist between particles? Yeah, so silver, okay, is going to be metallic bond. Okay, and then the iodine between iodine molecules. So be careful with this. Okay, I2 and I2, they are bonded with van der Waals forces of attraction, not covalent bond. Yeah, covalent bond is between I and I. Yeah, so that's going to be D. 11, which physical property is not caused by hydrogen bonding between water molecules? Okay, the answer is A. Why? Because the bond angle, okay, of water, okay, it depends on the two bonding pair of the electron and two lone pair of electron. Nothing to do with the hydrogen bonding. But whereas when you look at the water has higher boiling point than H2S, H2S does not have hydrogen bonding. Water has hydrogen bonding. So therefore, it's hydrogen bonding. Okay, it's a reason. Water can dissolve in most ionic salts, yes, okay, because they can actually form hydrogen bonding. Hydrogen bonding, they will actually help, okay, to dissolve most of the ionic salts. And then ice floats on water. This is going to be to create the open structure, because whenever in ice, okay, when ice is formed, okay, hydrogen bonds can be formed where it creates the open structure that will increase the volume. So the density will be slightly decreased for ice. Yeah, so that is actually also correct. Yeah, so that's going to be the answer for AM. Okay, now for 12, okay, for 12, okay, the three elements, okay, have the physical property as shown in the table. So we have this lower melting point here for X, lower melting point. It means that at 25 degrees Celsius, they already melted. Okay, so it means they must be liquid. Yeah, so and then they haven't boiled yet. Yeah, so iodine is solid actually, so this answer will not be accepted. Yeah, so this one liquid. Okay, we know that bromine is going to be liquid, so possible. Okay, and then we compare. When we look at the Y and Z over there, okay, Z has a higher melting point and boiling point. Okay, and then when we look at the density wise also, okay, the density of Y is smaller compared to Z over there. So in this case, okay, and then the difference between the melting point and boiling point, they are not so big. Okay, so the answer most probably is this one, because the boiling point and melting point, this one depends on the metallic bonding. Okay, when you have Na plus, if you're comparing with Mg2 plus, magnesium has more metallic bonding, okay, because of the more charge, more electrons. Okay, so that's going to be more metallic bonding. So boiling point and melting point will be slightly higher. Okay, but when we look at the density wise also, it matches. Okay, Y is going to be lower density compared to Z over there. For aluminium and silicon, okay, for aluminium generally, Y is supposed to be yeah, the density is going to be lower, but density and boiling point for silicon should be way higher. Yeah, way higher than this if it is going to be silicon. Okay, so and then the density might be way higher also. So anyway, so the answer will be B for this. For this one, we need to calculate. So you have a rock of 1 gram. Okay, so 1 gram, and then it contains calcium carbonate. So calcium carbonate, they will react with the ACl. Okay, so I write down the equation: calcium chloride plus carbon dioxide plus water. So if I balance the equation, just put 2 there. So it means that 1 mole react with 2 moles. Okay, so I can find out what is the number of moles of this. Okay, so 18 times 0.5 divided by 1000. So I will get 9 times 10 to the power of -3. So because of 2 moles and 1 mole, okay, therefore this will be half of it. So 4.5 times 10 -3. And then what I need to do next is to try to find out, okay, the mass of calcium carbonate. The mass of calcium carbonate is going to be the number of moles, which is 4.5 times 10 -3. You times with the MR, okay, of the calcium carbonate. So this one, you find out the MR of calcium carbonate is going to be 100. Okay, so This one is going to be, you will get, hold on, yeah, 4.5 times 10 negative 3 times 100. So you will get 0.45. Correct. So after that, okay, you find out the percentage. So it's going to be 0.45 is calcium carbonate out of 1 gram of the rock, okay, times 100%. You will get the answer as 45%. Done. Now, butane burns in air according to this equation. So you need to know that butane, okay, is actually a gas. Okay, they are gas. This is also gas. Carbon dioxide is also gas. When you burn something, this is going to be released in form of steam. So whenever we are reacting something and then they are in gas, we have also learned about PV equals to nRT. You can rewrite this. PV equals to PV divided by RT equals to N. If let's say they are measured at the room temperature and pressure, means the pressure and the temperature, they are constant. R is also constant. So we can say that V is directly proportional to number of moles. So in simple terms, okay, if let's say you are using 30 cm cube over here, you do not need to find out the number of moles, okay, because it's directly related to your volume. So we can actually just calculate directly. You want carbon dioxide, yeah. So if you have 2 gives you 30, so this is 8. So the ratio is going to be 4, okay. So it means this one should be 4 times greater than 30. So 30 times 4, that's going to be 120. So this is going to be, the answer is going to be B. Very easy, yeah. Now, next question, which mass of the gas has the least number of molecules? Okay, so first of all, we need to calculate the number of moles, okay? How do we calculate the number of moles? Okay, 3.2 divided by oxygen is 16, so 32, so you will get 0.1. 5.6, okay, nitrogen is going to be 14, so 14 times 2, 28. So this one, okay, 5.6 times, hold on, yeah, 5.6 divided by 28. That's 1 over 5, so 0.2. And then this one will be 8. 32 plus 32, 16 plus 16, yeah. So 8 divided by 64. Okay, so 8 divided by 64, that's going to be 1 over, okay, 8. So 0.125. 11 divided by 44. Okay, 11 divided by 44, that's 0.25. So here, when we want to find the number of molecules, okay, just times with the Avogadro constant, yeah. So since they are not talking about atoms, so we no need to times like 2 times by 2 times by 3 times by 3 and so on. So in this case, we just can refer to the number of moles over here, okay. So no need to times with an Avogadro constant. You just can see which one is the smallest value of the number of moles. So I can see the answer is going to be 15. Yeah, 15 is the answer. Now, so that is going to be, sorry, the answer is going to be A. Yeah, 15, the answer is going to be A. Now, so 16, okay, is a very interesting question because they are asking which is the bond angle, which is going to be the largest. So here, if you want to answer this question, you need to be very careful. If it is carbon, carbon generally form 4 bonds. Okay, but if they have double bond or triple bond and so on, we always calculate the the double bond, we calculate 1 as 1. So triple bond, we also calculate as 1. We will take only the sigma bond. So here, like for example, here, 1, 2, and then we take only 1. Okay, so there are 3 bonding pair. Okay, 3 bonding pair, they will actually form trigonal planar 120. So here carbon also 4 bonds. So you see 1, 2, 3, 4. So this is going to be tetrahedral. Okay, but other than carbon, so whenever we are dealing with other than carbon, you need to be extra careful because here 1 bond, another bond, another bond. So 3 bonding pair, but do remember nitrogen is group 15. So they have 5 valence electron. 1 valence electron, okay, another 3 valence electrons are used for bonding here. So there should be another 2 valence electrons over there. So there is 1 lone pair. Okay, so when you have this situation, this should be a pyramidal shape. So pyramidal shape is similar to ammonia. So this is 107 degrees. The same thing applies for D over here. Okay, we are dealing with oxygen, different than carbon. So two bonding pair, and it don't stop over there, because do remember oxygen is group 16, 6 valence electrons. So 1, 2. Okay, so another 4 electrons they are outside. Okay, so it means there are 2 more lone pair over there. So 2 bonding pair and 2 lone pair, that will actually give you the bend shape. So this is 104.5 degrees. So if you look at all these angles, which one is the largest angle? Okay, comparison. So the largest angle will be A. So that's going to be our answer. Okay, next. Which structural isomer has the highest boiling point? Do remember all of them actually have OH over there. They do have hydrogen bonding. So when it comes to hydrogen bonding, we just comparing, like for example, here you can see all these are branches, okay? They are branches, okay? And then the only one that do not have branch is going to be B. So this is the answer, because if you want to actually form something that has more boiling point, okay, if you are comparing branching and non-branching, the longer, okay, structure, okay, generally they will have higher boiling point. Okay, so in this case, definitely going to be the answer is going to be B. Okay, next. In which change will only van der Waals forces have to be overcome? Evaporation of ammonia. Ammonia has hydrogen bonding, so no. Okay, melting of ice. Okay, if you want to melt ice, ice has hydrogen bonding. Okay, you need to actually overcome that as well. Okay, melting of solid carbon dioxide. Solid carbon dioxide, they are non-polar. Okay, they are non-polar. So since they are non-polar, then there is only van der Waals forces for them. Yeah. Solidification of butane. So solidification, in this case, we are not overcoming that van der Waals forces. In this case, we are trying to make them as a solid. So they are more towards forming the bond. So in this case, we are overcoming. So the best answer is going to be C. Okay, which gas closely approaches ideal gas behavior at room temperature and pressure? So if you look at here, ammonia definitely will not be the answer. Okay, carbon dioxide, okay, it's going to be non-polar. Hydrogen is non-polar. Helium is non-polar. So let's actually look at the intermolecular forces over here. So we don't want a lot of intermolecular forces. In this case, carbon dioxide, if you compare with hydrogen and helium, will not be considered because it's slightly bigger. It has more electrons. Okay, now if you look at hydrogen, hydrogen is exists as H2. So each of them, they have 1 electron. So total electron, they have 2 electrons. And then helium is the electron is also 2. Okay, and then the mass is 4. So we don't actually just refer to, oh, helium is actually bigger mass than helium is the answer. No, whenever we actually use that is actually an assumption. Yeah, so bigger. So we tend to actually say if you have more mass, then generally they are bigger, more van der Waals force. But actually what they are looking at is the number of electrons. So they do have the same number of electrons. So we want it to be more ideal. So if it is more ideal, we just narrow down hydrogen and hydrogen. They tend to be a molecule. And then if it is going to be helium, helium and helium, they are inert. Okay, they don't actually mix well with the others, so they don't react. Yeah, so in this case, the best answer over here, the ideal gas behavior, is going to be helium. Okay, helium, no intermolecular forces. Okay, and then the distance are far greater from each other and so on. So helium will be definitely the best answer for this. Next question. So you have PV equals nRT ideal gas equation, and then certain all the information I given. So what we need to do, we just need to use the formula. Okay, so we want what is the pressure. So pressure we want to count. The volume, okay, is given in meter cube, so no need to convert. Okay, so you just put in there. Number of moles. Okay, so this is oxygen gas 0.96. Oxygen is going to be 16 and 16, so 32. R is 8.31. Temperature must be in Kelvin, 30 plus 273. So it's going to be 303. So use this formula, find the pressure. Okay, so quickly I'll just calculate. Okay, then I calculated to give you 10791. Okay, so if I change it into kilopascal, so this is Pascal, 10.8, okay, kilopascal. Okay, so that will be the answer, C. Okay, 20 is C. So 21, okay, let's move on. So which equation shows the reaction that occurs during the standard enthalpy change of atomization? So you need to understand, okay, the atomization, we are trying to change iodine into atom, okay? So we want atom of iodine, okay, in form of gas, okay? So atom of iodine, okay? But do remember I2 to give you 2 moles of atom of iodine. Yeah. So enthalpy of atomization is going to be the energy required, okay, the enthalpy change, okay, to form 1 mole, okay, sorry, then to form 1 mole of atom, okay, 1 mole of atom, okay, in gaseous form, okay, from the elements in the standard state. So the element, when they were element in standard state, iodine was in solid form. Okay, so if you want 1, I2, so the best answer is going to be C. Okay, so that's going to be the answer. Okay, you need to know how to define, yeah. Okay, definition is very important. So what enthalpy of atomization is to energy change when 1 mole of atom in gaseous state is formed from the elements under standard condition. Yeah, so do remember that. So iodine is solid, bromine is going to be liquid, okay, chlorine is going to be gas, okay, and so on. So here, reaction pathway, reactant and products, you can see reactant is higher energy than the product. So definitely this is going to be energy being released. So it's an exothermic. So they are asking which of the following are not exothermic. Okay, so we know that neutralization is exothermic. Combustion is exothermic. Formation, you want to actually form something, yeah. And then you have also the atomization. So which one doesn't apply to? So this one you need to be, you need to understand formation is not always going to be negative. We cannot just look at the formation and say, okay, formation is going to be bond forming. Bond forming is going to be release of energy only. No, not really. Yeah, but enthalpy change of atomization, for example, I2, I want to change it into I. Okay, so if I want to change into I, what I need to do? I need to break the bond. Yeah, I need to break the bond over here. So here, okay, hold on. The enthalpy change of formation is always going to be, okay, always going to be forming bond formation. Okay, always going to be bond formation. So you are going to actually to form something. So it's going to be always going to be exothermic. Okay, exothermic. And then enthalpy change of atomization. Okay, to change into atom. Okay, to change into atom is going to be always involves bond breaking. So this one is going to be endothermic. Okay, it's going to be endothermic. So it doesn't apply to this. Okay, but enthalpy of formation. Okay, let me check enthalpy of formation. Is it going to be always exothermic? Okay, so you see, in this case, enthalpy of formation can be positive, can be negative. So please actually remember that. Yeah, but enthalpy change of atomization always endothermic. Yeah, so please remember this. Okay, we don't have any issue for enthalpy change of neutralization and combustion because they are always going to be exothermic. enthalpy change of, let's say we are talking about decomposition reaction and so on, they are always going to be endothermic. So for atomization is always going to be endothermic. Formation can be either positive or negative. Okay, take note of that. Now, in an experiment, okay, so this one is going to be Q equals to MC delta T. Okay, the burning of certain number of propanol was used to heat 100 grams of water. Okay, so we use Q equals to mass of water. Okay, 100. The initial was 25, final temperature is 83. So you just need to find the difference of the temperature. No need to convert into Kelvin because we are just finding the difference. 58 is the difference, delta T. And then the C, we will use 4.18. Okay. So you just need to calculate. Do remember it's an increase in temperature. So enthalpy change must be negative. All of them are negative, so no issues. Okay, 100 times 4.18 times 58. So you are going to get 24244. Okay, that's going to be joule. And this is going to be for 0.025 mole, okay, of propanol. They will give you 24,244 joule. So I want for 1 mole, okay, of propanol. So you just need to divide, okay, 24,244 divided by 0.025 for 1 mole. You are going to get 969760. You can change it into kilojoule. So 96970. Okay, 970 kilojoule, and it's negative because it's an exothermic. So the answer is going to be C. Okay, next. Okay, now so let's actually pick up some speed over here. Yeah, titanium, okay, occurs as a mineral. Okay, so one possible method, okay, is by heating with carbon. Okay, standard enthalpy change of formation. Okay, this one is my method. I really like to use this method. Okay, formation of this is going to be negative 940. Enthalpy change of formation of this, so because there are 2 moles, so 2 times negative 110, so negative 220. Okay, and then titanium, okay, and then carbon, they didn't give you any value over there, but do remember elements, you do not need to have any energy of formation, enthalpy of formation, 0, 0. So we just want to find what is going to be this enthalpy change. So this one, just put, okay, a circle there. Okay, clockwise equals to anti-clockwise, 940. This is clockwise. Clockwise plus 0 plus delta H equals to 0 plus negative 220. Delta H, negative 220 plus 940. So just calculate. The answer is going to be 720, and it's actually positive. So the answer is C. Okay, 24 is C. Let's move on. So here they are asking you to calculate the oxidation number. Okay, let's actually calculate the oxidation number. I think if you know like Cl2, oxidation number is 0, 0. So you can eliminate this. Okay, and then for sodium chloride, I think this one is quite easy also. Sodium chloride, the oxidation number is going to be negative. The oxidation number of chlorine in each of the following. Yeah. So I think this one, Cl2 is 0. Okay. And then sodium chloride, okay, the oxidation number of chlorine is -1. Yeah, correct. Okay, -1. And then this one, if you want to calculate, you can calculate. Okay, so this one is 1 plus x plus 3 times -2 equals to 0. X equals to -6 plus 1, -5. So x equals to 5. Okay, so that's 5. Okay, C. Next. So you have this equation. So I'll teach you how to do it very fast. Okay. 2 electrons, 6 electrons. So you need to times everything by 3 here. So times 3, 6. Okay. So you need to look for the ethanol that has 3. So you can see 3 is here. 3 is here. 3 is here. Okay, and then the 14, that's 14H. I didn't do anything about the H plus, but do remember 14H and then 6H is there on the right hand side. So it's going to be 14H minus 6H. Okay, if you bring to the left. So that's going to be 8H. Okay, so probably this will be the answer. You double check. Okay, this one, the rest is going to be 2, stay the same, 7. Okay, and then I times by 3, this one will be 3. So the answer is going to be A. Okay, 26 is A. If you cannot see, then you do the normal method. Yeah, just write down everything so that to prevent any mistake. Okay, I will move on. So here, when the gaseous iodine is heated with hydrogen, equilibrium is established. Which change of condition will cause the purple color to become darker? Now, when the purple color become darker means we want which of the following will actually make the position of the equilibrium to go to the left-hand side. So that is what we want to do. So in order to do that, okay, what we need to see is we need to find out, okay, what will be the, like for example here, the reactant, okay, we do have number of moles 2, and then the number of moles of HI is going to be 2. Okay, let me share the screen again. Okay, let's actually continue again. Okay, now, so V1, okay, for number 27, we want the position of the equilibrium to be shifted to the left, okay. How do we make the position of the equilibrium shift to the left? So when we look at the number of moles, there's 2 and 2. So I don't think so. If we change any pressure, it will affect because the number of moles are the same. So no effect. So here we just can look at the temperature. So when we look at the temperature, so we just see this one is going to be endothermic. So this is going to be cold. This is hot. So under what condition I want to actually move to the left from cold to become hot. So what I'm trying to do is I'm trying to increase the temperature. Why I am increasing the temperature? Because, okay, the change in the equilibrium into the previous equilibrium was you try to decrease the temperature. So the answer is going to be decrease the temperature. Or you want to double check, you can also double check. If you have decrease in temperature, what will happen according to LCP, you need to increase the temperature. How do you increase the temperature? By moving from cold to hot. So you happen to move to the left. So that is going to be the answer B. Yeah. So the next question, okay, you have we are going to look at the Kc, okay, but one thing that we need to take note whenever we are calculating Kc, we do not include solid. Okay, so aqueous solution was prepared, okay, certain number of moles, okay, in 1 dm cube of water, okay, then, so this one we can actually use the ice method, okay, so Ag plus Fe2 plus Ag solid plus Fe3 plus ice method. Okay, initially you have 2 moles of Ag plus, 2 moles of Fe2 plus. So initially there's nothing. When equilibrium is established, 0.88. Okay, so 0.88 was there. So what happens here is, okay, from 2 to become 0.88 is going to be, there is a decrease of, sorry, 2 minus 0.88, there's a decrease of, hold on, minus 1.12, okay, 1 mole, 1 mole, 1 mole, 1 mole. So this is also minus 1.12. This, on the other hand, will be plus 1.12, plus 1.12. So you just put there 0 plus, okay, so this is also going to be 0.88, 1.12. Okay, since we are not including Ag, just be careful here. Kc equals to Fe3 plus concentration divided by Ag plus concentration and concentration of Fe2 plus. So if I put in all the value, okay, so Fe3 plus is 1.12 1, 2 divided by 1. And then divide by 1 means the 1 dm cube. So Ag plus is 0.88 divided by 1, 0.88 divided by 1. Okay, if I calculate 1.12 divided by I will get 0.154. Let me see. This one. Fe2 plus should not be. Fe2 plus is 0.88. Ag should not be in. Fe3 plus there. 1 divided by this. Numerical value. Let me calculate again. 1. Fe3 plus is 1.12. 1.12 divided by 0.88 times 0.88. So I get 1.45. 28. The answer is B. 0.97. Aqueous solution, a mixture of 2 in 1 dm cube when the equilibrium was established. There was 0.88 in the mixture. When you have Ag plus 2, 0, 0. So 0.88 Ag plus 0.88. And this is correct. This is also correct. It's plus, this is plus. Okay, so when I calculate Kc is going to be this divided by these two. I think the answer should be 1.45. Okay, 28. Okay, the answer is 1.45. Okay, if I'm wrong, then let me know as well. Okay, but I think the answer is 1.45. Okay, maybe let me try again. Two moles. 0, 0. When equilibrium was established. Unless they are talking about a mixture of 2 moles in 1 dm cube. A mixture of 2 moles and 2 moles of everything in 1 dm cube of water. Together they are 1 dm cube. No problem. Divided by 1. Minus chem. Okay, let me just calculate them. Okay, so this one is going to be when you minus, okay, 1.12, you minus 1.12, you will get this. Ag solid will not be included. Okay, Fe3 plus, so Fe3 plus is going to be 1.12. 1.12 divided by 0.88 times 0.88. 1.45. Okay, that will be the answer.